Ospf is very picky and very critical about defining network types. In other words, when you use the network command in Ospf, and Ospf looks around and says, here's an interface on my router, its IP address falls within this network of this network command. Ospf doesn't just say, okay, I'll start sending out hello packets on there. The very first thing it does, it says, what kind of a link is that? And depending on the answer to that question will really dictate a lot of how Ospf treats that link and operates across that link. So we're going to talk a little bit about that right here. So when Ospf finds a link that's covered with your network statement, step number one is Ospf looks at the layer 2 encapsulation type. You see, a lot of other routing protocols could care less. EIGRP, RIP, they could care less whether it's PPP or HDLC or Ethernet on a link. They could care less. Ospf, that is important. So Ospf is going to look at the layer 2 encapsulation type, and using that is going to discover what kind of a network, what network type is on that link. Now, why is that important to Ospf? As it says here, it's important because it answers some very critical questions that Ospf asks itself. Number one, Ospf says, is this type of a link, will this link support me creating a multicast hello packet, sending it out there, and can I reasonably expect that everybody on that link will see it and respond back to me with their own multicast hello packets? Yes or no? Some link types, the answer to that is yes. Other link types, the answer to that is no. Cannot dynamically discover neighbors that way. Have to do something else. How many neighbors are expected to be on this network? For example, if it looks at the layer 2 encapsulation and says, oh, this is the point-to-point protocol, it's PPP. Well, PPP means point-to-point, me and you, and that's it. So if I define this link as point-to-point, that means I only expect to see a hello packet from one person, one route on this link. That's it, because that's point-to-point. Is there a need for the election of a designated router or a backup designated router? Some link types that support 3 or more routers on a link need this. Other link types like point-to-point links don't need this. So let's take a look at what these link types are. And by the way, there is actually an Ospf interface command that you do on your interface where you can manually tell it what the network type is. But by default, it will look at whatever your encapsulation type is, Ethernet, HDLC, PPP, and it will dynamically derive the link type based on what it sees there. So what are the network types? We've got broadcast, which is such as Ethernet, token ring, and FDDI. So on a broadcast link, we need designated routers and backup designated routers, so that election process will happen in the background. We have point-to-point links. So if it sees that you've got a loopback interface or PPP or HDLC, it will say, this is just me and one other person. Now, as a matter of fact, what's kind of interesting is that Cisco routers, I can't speak for non-Cisco routers, but Cisco routers actually classify loopback networks as loopback. You'll actually see in the network type, it'll say loopback. Nowhere in the Ospf specification does it actually say that. In the Ospf RFC, there's nowhere in there that says a network type of loopback, but Cisco does that. But here you can see I've sort of lumped loopback interfaces along with PPP and HDLC as point-to-point interfaces. Then we have non-broadcast multi-access interfaces. In my last video, I gave you an example of this one. I said, think about your connection to the internet. Okay, so you're at home and you've got a DSL modem or a cable modem or some kind of connection to your internet service provider. And although that one connection could lead you to multiple places, you can't put a broadcast frame on there and expect everybody to see it. It doesn't work that way. Another classic example of this is frame relay. So in frame relay, you've got this concept of you have a router and it's connected to some sort of WAN cloud. It has one physical link, and maybe there's 3 other routers that also connect to that frame relay cloud. Maybe these are routers that belong to, different campuses of this company. spread across your country, your state. And in a frame relay network, this router 1 knows, okay, well, when I put a frame relay frame on this wire, if I want it to go to router 2, I have to put a certain number on here. It's called a frame relay delcy. And if I put that number on it's part of the frame relay header. If I put that number on there, then my frame relay provider will know that when they see that number, it should go over here to this guy. If I put another frame on here and I put some other number like maybe 103, my frame relay provider knows that will go over here to router 3. And maybe if I put another number on here, 104, that will go over here to router 4. So in this particular case, every frame that you're putting on this wire is going to one place based on what the identifier, the delcy identifier, is in that frame. So like Ethernet, this one wire, this one cable you have here connecting to your WAN could take you multiple places. But unlike Ethernet, there's no way to create just one single frame and have all 3 remote devices see it. That's impossible. The nature of frame relay says you got to put your delcy number on there, and that will have it go only to one location at the other end of the cloud. So that's considered a non-broadcast multi-access medium. That also does require a designated router and a backup designated router to be elected. And then we also have a point-to-multipoint network type. Now these first 3 types that we've looked at, broadcast, point-to-point, and non-broadcast multi-access, these are all dynamically derived. I should say dynamically determined. So all OSPF has to do is take a look at the encapsulation on the interface. If it's any one of these, then it knows, okay, I know what the network type is. Now, point to multipoint, the only way it will ever learn that is if you tell it. So as a network administrator, you actually have to go onto the interface and use an OSPF command to say, this is a point to multipoint network. And an OSPF point to multipoint network is defined as a numbered point-to-point interface having one or more neighbors. That is a point-to-multipoint network. So just to give you an idea as to what that would look like, a classic example of a point-to-multipoint would be where you have a WAN interface, like a serial interface, serial 0/0, and you decide to create a sub-interface out of that. You might remember back in the time when you were learning about switching and we were talking about inter-VLAN routing, we said, well, if you want a VLAN trunk extended to your router and you want that router's interface to service multiple subnets, that router's fast Ethernet interface has to be broken up into several sub-interfaces, logical interfaces. Same thing is true here, except on a WAN interface. So we're taking our serial interface, we're giving it a dot, and then putting some number on it. Now, when you do that, if you hit enter, Cisco IOS will say, incomplete command. I need more information. So after that, right here, you have to define, Cisco IOS will give you 2 choices. You could either say point to point, in which case OSPF will say, aha, that is a point-to-point network type, no problem. Or your other choice is multi-point. So this is right when you're creating the sub-interface in the first place. You have to use one of these 2 keywords after the number of your sub-interface. Now, if I choose multi-point, you might think to yourself, oh, okay, then OSPF will dynamically determine that this is a point-to-multipoint interface, right? Wrong. Remember, I said OSPF cannot dynamically determine point-to-multipoint interfaces. You have to configure it. So if OSPF sees a sub-interface that is multi-point, it will assume it is non-broadcast multi-access. It will assume it's that kind. So if I want to say, oh no, you're point-to-multipoint, I have to actually write in here I have to say IP OSPF network. I'm going to write down here because I'm running out of room. Point to multipoint. I actually have to type that in under my subinterface. And now OSPF has been told explicitly what kind of a network it is. One additional thing I want to say about these network types before I leave this. Of all of these network types, broadcast, point-to-point, and point-to-multipoint all allow for dynamic neighbor discovery. They all allow for dynamic neighbor discovery. So it will just send out an OSPF hello packet going to 224.0.0.5 and dynamically discover neighbors. The one exception to this is non-broadcast multi-access. In a non-broadcast multi-access network, you as a network administrator have to manually tell OSPF which neighbors you want to talk to. It's actually a neighbor command. Neighbor 1.1.1.1, neighbor 7.4.37.2. You have to tell it what neighbors. It cannot discover it dynamically on non-broadcast multi-access links. A couple more things here. Router roles. In OSPF, a router will play one or more of these roles. So let's take a look and just see what that's referring to. Let's say that I have all of these links here in an area. So we'll just say this is area 1. Okay? So if a router has all of its links in one area only, we call that an OSPF internal router. And that's all that means. An internal router simply means all of its links are in one area. What area, Keith? You might ask me. It doesn't matter. It doesn't matter if it's area 0, area 1, area 90. Just the fact that a router has all of its links in one area means it's an OSPF internal router. So in this particular case, R3, switch 3, and R4 would all be considered OSPF internal routers. Now furthermore, let's say that I actually now have two areas like this. And remember, if you have two or more areas, one of them has to be area 0. It's got to be the backbone area. Okay, so which routers in this diagram are OSPF internal routers? Well, hopefully you said every single device except for switch 2. Switch 2 is the only device in this particular case that has some links in one area and some links in another area. So switch 2 is not an internal router. All these other routers are internal routers. Another type of router is a backbone router. A backbone router simply means a router that has at least one link in area 0. So these four devices here, R1, switch 1, R2, and switch 2, they are all considered backbone routers because they all have links in area 0. R1, switch 1, and R2 not only are backbone routers, they're also internal routers. They're both. And in a previous video, we already talked about an area border router, which is a router that has at least one link in area 0 and one link in a non-backbone area. So in this particular case, switch 2 would be an area border router. And then the last type of router, let's say that we had a router right here, router X, that was connected to switch 3, and these two guys were doing something that was not OSPF. Maybe it's RIP. Maybe it's EIGRP. It doesn't really matter. The point is, switch 3 is learning about routes via some non-OSPF method. And then switch 3 says, okay, I got to take these routes that I learned via RIP or via EIGRP, and I need to convert them into OSPF routes. We call that redistribution. I need to redistribute these RIP and EIGRP routes into OSPF so my OSPF neighbors will understand them. So he creates LSAs out of that. So now switch 3 is considered an autonomous system boundary router, an ASBR. That is switch 3. He is an ASBR, autonomous system boundary router. That is a router that's redistributing routes into OSPF that were learned via some non-OSPF method. That's an ASBR. And lastly, let's just talk real quickly about the tables and data structures that OSPF uses. So just like EIGRP, OSPF has a neighbor table, keeping track of neighbors. In OSPF, when a router receives OSPF LSAs, it stores them in what's called the link state database. So the link state database is a loose collection of all the LSAs that you've got, and you can view that. I'll show you some commands in an upcoming slide series on that. Then OSPF sort of takes those link state advertisements and pieces them together into a topology, and we call that the SPF tree. There really is no command to view that. There's no command to actually see from the router's perspective what the SPF tree looks like. It knows in its CPU, but there's no commands that we can see that. And then of course there's the routing table. Once the SPF tree is built and the shortest routes are derived to any given destination, those routes may make it into the routing table. Once again, it's dependent on factors like administrative distance and any potential route filtering that we might have in place.